Alright, welcome back to Math 332. In this video, we are going to look at a computational example. In this case, we are given the four matrices here, and you are asked to show that these four matrices actually form a basis for this vector space M2 by 2. So in order to show that these four matrices form a basis for that vector space, first we will have to show that the span of all these four matrices is actually the entire M2 by 2. That is to say that you have to show that every element in this set can be written as a linear combinations of these four matrices. Okay, now second thing that you need to show is to show that these four matrices are actually linearly independent. That is, if you set up these equations, then the only solutions for the C1, C2, C3, and C4 are the trivial solutions. If you look at this equation, you know that if you set C1 0, C2 0, C3 0, C4 0, this left hand side here is obviously the zero matrix, which is equal to the right hand side. These are known as the trivial solutions, okay, the obvious one. So if the only solution for this equation are the obvious one, then they are linearly independent. If somehow you can find that C1, C2, C3, and C4 they doesn't have to be all zero, which means some of them can be non-zero, and you can still have this, then we will have to conclude that the four matrices are linearly dependent, which means they are not independent, okay? So since we've been asked to show these are the bases, so we are anticipating that the only solution here are the trivial one, the obvious one, okay? So let's look at how do we show the first part, okay? So in order to be a basis, it has to satisfy that two conditions, okay? So now we are looking at the first one. So we want to show that the span of all these four matrices is actually the entire vector space M2 by 2. So as I said before, what you need to do is to pick one element from here, a fixed but arbitrary elements, which we call A, B, C, and D, and we want to show that it is possible to find C1, C2, C3, and C4 such that this thing here will equal to A, B, C, D. Okay, so you write out the equations. So from here, if you look at the first component here, you have a C1 plus C2 plus 0C3 plus C4 equal to A. That's how you get the first equation. You look at the second component here, C1 minus C2 minus C3 plus 0C4 equals to B. That gives you the second equation. So this is how we get these four linear equations coming from these four components of this matrix operations. So again, let me remind you that we have to find C1, C2, C3, and C4. You do not have any control of this A, B, C, and D. So these are arbitrary numbers and they are fixed from before. So you have no control of this, okay? Now, instead of looking at the systems, we can put it into a matrix form. So this is the same as the one that we have before. Now, we don't want to try to row reduce this entire thing. If we want to row reduce this, when we put it into an augmented matrix and try to row reduce this, then you have to deal with the A, B, C, D, okay? So your calculator will not be able to deal with it, and you will have to do it by hand. It will take a long time, and it's going to be a mess. So another alternative is that the coefficient matrix here is a square matrix, which means there's something else that we can do, which you're going to see in a minute. So we look at this coefficient matrix and try to row reduce only the coefficient matrix. So this is nice, they're all numbers. So the row reduced echelon form is actually the identity matrix, which means the coefficient matrix here can be row reduced to the identity matrix. From what we know before, that implies that that matrix will have to be invertible, okay? So let us call this matrix A. So we have matrix A, and the systems that we have before is actually just matrix A multiply this equal to this. So because your matrix A is row reduced, can be row reduced to the identity matrix, so we know that it is invertible, which means that we invert this matrix, multiply A inverse here, multiply A inverse here, and you will see that C1, C2, C3, C4 actually is going to be equal to this, whatever this thing is. So theoretically, from here, you can already tell that your C1, C2, C3, C4 exists. You can find those numbers such that you will have this equality, okay, which means that you will have this system, and you will have C1, C2, C3, C4 such that this thing equal to A, B, C, and D. So theoretically, if you can see that is very good. But for some of you, this might be new, so you can't really see what happened. Like, why is that having this implies that we are done, okay? So if you have these problems, I'm going to show you all the computations, which you do not really have to do in the exam, by the way. I'm just showing you so that you can see what's going on. So remember that we call this matrix A, right? So we can actually compute A inverse explicitly. So the A inverse is going to be this. That's the A inverse, okay? So your C1, C2, C3, C4, as I claim, is A inverse multiplied this. If you multiply this matrix out, you will see that your C1 will have to be D, your C2 will have to be this, your C3 will have to be this, your C4 has to be this. Which means if you put it together, this is your C1, this is your C2, this is your C3, this is your C4, then you can see that we can actually find corresponding C1, C2, C3, C4 such that this equation will hold. That is to say that this matrix is really a linear combination of these four matrices. Okay, these four matrices. These are numbers, these are numbers, these are numbers, these are numbers. So if you see something that looks like this, immediately you conclude that this matrix is a linear combination of these four matrices. Okay, so we see that it can be done. You don't really have to do this computation. As I said, this is enough. This is enough. Okay, if you cannot see it, now you see it. Okay, now you see explicitly how this thing works. And next time, you don't really have to find the A inverse. Okay, you don't have to find A inverse explicitly. You don't have to find all this thing explicitly. You can immediately conclude from here that the span of all that four matrices is really the entire this vector space M2 by 2. Okay, now that's the first part. Now the second part is to show that they are linearly independent, which means that if you set up these equations, we want to figure out whether or not the solutions are the trivial solutions. Okay, if you set up these equations, you want to figure out whether or not the solutions are the trivial solutions, are the only solution are the trivial solutions. Okay, so you don't have to repeat all the computation. You remember that we just computed something similar with A, B, C, D. Now your A, B, C, D are all 0. Okay, so you set this thing up and you can see that last time you have A, B, C, D, now you have all 0. Same reasoning, same matrix, same coefficient matrix. Nothing changed of the coefficient matrix. The only thing changed is here. So the coefficient matrix is still the same. So you recall a minute ago that the coefficient matrix can be row reduced to the identity matrix, which means the coefficient matrix is invertible. So which means from here, you can also immediately see you have no choice whatsoever for C1, C2, C3, and C4. They all have to be 0. If you set this thing up, they all have to be 0. That by definitions, those matrices are linearly independent. So if they span the entire space, the four matrices, if they span the entire space and they are linearly independent, then we call this four matrices basis. They form a basis for this vector space. That is the definition of basis. All the vectors that satisfy these two conditions form a basis for that vector space. And that is what we want to show. And that's the end of this video.